Welcome, this is Dr. Plague, and today we're going to take a quick look at implementing circular buffers in the C programming language. Why, you may ask? Well, I'll be using these files in future videos when I start working on projects that use microcontrollers. For example, I will be making a flash memory programmer which will use a collection of different files, so breaking this up into several videos will help make those videos shorter. Bear in mind that there are many ways to implement a circular buffer, and I'll just be showing you one way that I do it. This will just be a quick and simple implementation. Now, just as a disclaimer, I'm an electrical engineer and not a software engineer. Although I have been writing code for many years, it is not my main forte, so don't expect my code to be stellar or anything. Many of you may be able to write much better code than I can. So, if you're not familiar with a circular buffer, it is simply a memory structure where data is stored in a first-in, first-out manner. But what makes a circular buffer special is that the memory wraps around from the end back to the beginning, kind of like in a circle, meaning there is no end to the buffer. Let's pretend each of these locations represent 1 byte in memory, and let's say we have some data stored in this buffer. Let's say we first place the data value of 10 here, then 8 here, then 13 here. There will usually be a couple data pointers or indexes associated with a circular buffer. One that points to the memory location where we are going to insert data, and one that points to the memory location where we are going to pull data out of the buffer. And since this is a first-in, first-out data structure, we'll point the index that reads the data to the first byte that was stored, right here. These indexes are commonly called the head and the tail. Now, I've seen circular buffers implemented 2 different ways. The way I implement a circular buffer is that I add data to the head and remove data from the tail. Most people probably do it opposite from this, meaning that they add data to the tail and remove data from the head. But to me, this makes no sense, because if you think about an animal, for instance, food goes into their mouth, which is usually on their head, and it comes back out their tail end. Food enters the head and gets spit out the tail, right? Now, I know there's been a South Park episode where they were shoving food into their rears, and it came out of their mouths. But that's just wrong on so many levels. So, I insert into the head and remove from the tail. Think of it this way. Would you rather take data out of a buffer that's been regurgitated, or data that's been properly processed?
Oh, come on. You are so disgusting.
You're right. I'll just do this another way. I'll call the indexes the read and the write indexes. That way there's no confusion. So the write index will point to the memory location where we store the next byte of data, and the read index will point to the memory location where we extract a byte of data. Each time we write data to the buffer, we move the write index to the next memory location. And likewise, when we read data from the buffer, we move the read index to the next memory location. When the buffer is empty, these 2 indexes will point to the same location. So, let's say we want to store the number 10 into the buffer. We place that into the location where the write index is pointing, like this. Then, we move the write index to the next location. Now, let's say we want to store the number 8 into the buffer, so we do the same thing. Put it where the write index is pointing, and move that index ahead. Now, if we want to remove a byte of data from the buffer, we simply take the byte from where the read index is pointing, and we move the read index ahead. There is still 1 more byte of data in the buffer, so we could do the same thing to read that last byte. Now, we don't actually need to erase any data from the buffer when we read it. It can just stay there. It'll be overwritten the next time data is stored to that location. So this is how a circular buffer works. Now we just need to implement it in code. Now, one thing you might be wondering is, how do we make this buffer circular? I mean, memory is not circular, it's contiguous, with each location following the next, and it doesn't wrap back around, at least not normally. If we look back at our circular buffer, we could call this index 0, followed by index 1, all the way up to 7. So, if we increase our index from 7 to 8, then we need to subtract 8 from it so it points back to 0. There's an easy way we can do this in code if we use a buffer length that is a power of 2. And I'll choose a buffer length of 256, which is 2 to the power of 8. You can choose any buffer length that you want, but you will need to adjust the code accordingly. I'll show you how we can easily take advantage of a length of 256 when I create the code. Now, if you're using a microcontroller with very little memory, such as the ATmega48, which only has 512 bytes of RAM, then you probably won't want to waste half of the memory for a circular buffer, so adjust accordingly. I use a lot of ATmega 1284s, which has 16K of memory, so 256 bytes isn't such a big deal compared to the other microcontroller. Now, I'm going to create a new project in Atmel Studio, and I'll just call it Circular Buffer Test. I'll just pick a Mega 1284 since that's a common processor that I use. I'll create and add 2 new files to this project. One will be a .c source file, which I'll name circular_buffer. And the other will be a .h header file, also named circular_buffer. We'll start out in the header file. I'm going to add this here include. That will make sure we have all the data types that we need. Next, I'll make a structure to contain all of the data and indexes that we need. I'll create an array for the buffer data, and remember I said I wanted an array length of 256 bytes. Next, I'll create the 2 indexes, one for the write and one for the read. I'll make them 8 bits, so they can only hold values from 0 to 255. That way they can never hold an index value that is outside of the range of the array length. By making them only 8 bits, we don't need to make any adjustments when incrementing beyond the value of 255. If we increment the 8-bit value of 255, it'll just wrap around back to 0, since the value of 256 requires 9 bits, and the lower 8 bits of 256 are 0. So the most significant bit just gets thrown away. I do want to make the indexes volatile, so we don't need to worry about using this circular buffer inside an interrupt. This will just make sure that any code optimization does not optimize away any of the functionality. Next, I'll move to the circular buffer source code file. I'll be sure to include the header file so we can access the structure we just created. The first function I'm going to create is an initialization function. This function will not return any values. I'll name it cbuffer_initialize, and it will have one parameter, and that'll be the circular buffer structure that will need to be defined as a variable elsewhere in the user code. And this initialization will just set the read and write indexes to 0. We could also just copy one index to the other. It doesn't matter, we just need them to point to the same location in the array, so it starts out as empty. Now, if we were programming in C++, then we could just put this into a constructor. But since I'm using plain C, I will just create this initialization function. Keep in mind that if the structure is defined as a global variable, then we don't need to initialize it, since all global variables will be initialized to 0. I'll demonstrate this later on. Also, you may want to add comments into your own code to help document it for future purposes. I'm not going to add comments since I use these type of functions all the time, and I'm very familiar with them. Also, the names I use for the functions and variables are descriptive enough in my opinion. Comments are generally a good idea, but they can add clutter if you overdo it, so I generally only use them when needed. You'll see me adding comments to code in future videos where things aren't so easy to understand. Okay, I'll place the function prototype into the header file by just copying this and pasting it with a semicolon at the end. Now, I'll go back to our source file and create a function that will add data into the circular buffer. This function also will not return any values. I'll name it cbuffer_put, since it will put data into the buffer. It'll have two parameters. The first will be the buffer that the data will be added to. The second parameter will be the byte of data that will be added to the buffer. So, we said the right index points to the location in the buffer array that the data will be added to. So, I'll just use the right index as the index into the buffer and copy the data to that location. And of course, we want to increment the index afterwards. So, I'll just add a post increment to the right index. Now, let's place the function prototype into the header file and compile it to make sure we don't have any errors. And the build succeeded. So, we're good. Let's test out what we have so far. So, let's go to the main file and include the circular buffer header file. Now I'll just define a variable for the circular buffer, which I will name test_buffer. And let's initialize this buffer. We need to pass the address of the buffer to the initialization function. Hence, I placed an ampersand before the variable name. Now, I'll put a byte of data into the test buffer. And I'll choose the value of 10. I'm going to place a copy of the initialization function call into the while loop. This will provide a place for the simulation to pause after executing the cbuffer_put function. If I don't provide a place for the code to pause, then the code will continue executing until I manually pause it. You'll see what I mean when we simulate the code. Now, I'll just provide a breakpoint right here so that when we simulate the code, we'll have a place to start single-stepping. And I need to change the tool to the simulator before we begin running this code. I'll click this green arrow up here to start the simulation. And I'm going to add our test buffer to the watch window. And I'll do it twice since the buffer data shows up above the index values. This way I can display all the variables at the same time. So now we can see the two indexes along with the first 5 bytes in the buffer array. Let's single step this. But you know what? Before I do so, I'm going to change the right index to, let's say, 65, so we can make sure the initialization function actually sets this back to 0. We can just edit the value in the watch window. Now I'll single step over the initialization function. This will execute the initialization function and pause on the next line. Notice that the right index changed from 65 back to 0. That function appears to be working so far. Now, when we execute the put function, the value of 10 should be placed into the buffer array at the location that the right index is pointing to, which is here at location 0. Also, we would expect the right index to be incremented from 0 to 1. Let's execute it. And notice that 10 was placed at location 0, and the right index was incremented to 1. Beautiful! I'll exit the simulation and make a couple copies of the put function so we can add 2 more values to the buffer. I'll choose 8 and 13. Now let's simulate this to make sure we can add more values to the circular buffer. We added 10, we added 8, and we added 13. Also, notice that the right index now correctly holds the value of 3. Perfect. Let's stop the simulation and create our next function. I want a function to read a value out of the circular buffer. It'll return an unsigned 8-bit integer, and I'll name the function cbuffer_get. All we need to pass into it is the buffer that we want to get a value from. So all this is going to do is return a value from the buffer. We'll use the read index as our location in the buffer to read from. And of course, we want to increment the read index after we get the value. So I'll use a post increment. Now let's add the prototype to the header file. And we'll make sure it compiles. Great! Now we'll test out this new function. To do this, I'm going to add a new 8-bit variable called data, which will temporarily store the value returned from the circular buffer. I'll initialize it to 0 so we can see it change from 0 to a new value. I'll make this volatile so that the compiler does not optimize it away. Now let's add the get function right here, and we'll put the return value into the data variable. Notice that the compiler returns a warning that the variable named data is set but not used. We can ignore this because we are just using the data variable for debug and simulation purposes, as a way to peek at the return value from the get function. Let's simulate this. I'm first going to delete the second test buffer variable from the watch window so that I can add the data variable in between them. After adding the data variable to the watch window, I'll re-add the second test buffer variable to the watch window. There, now we can see the indexes, the data, and 4 bytes of the buffer. I'll simulate the code. Now, before we execute the get function, notice that the write index is 2, the read index is 0, and the data is 0. The read index should increment after we get the first byte of data, which is 10. Now, we'll execute it and notice that the write index was unaffected. The read index incremented to 1, and the data variable is showing the value of 10. This works perfectly. We'll place the last value into the buffer. Great! Let's stop the simulation and create one last function. This function will return the number of values stored in the circular buffer, which will be an 8-bit value since the buffer length is only 256. I'll call it cbuffer_data_available. And it'll only take one argument, which is the buffer that we are questioning. All we need to do to determine the number of available stored values is to subtract the read index from the write index. Since these are all 8-bit values, we don't need to worry about adjusting for any out-of-range or wrapped-around values. And I'll just add the prototype to the header file. Then I'll recompile it to check for errors. Now let's test out our final version of the circular buffer functions. I'll add another variable to store the number of available stored values in the buffer, and I'll initialize it to 255 so we can see it change back to 0 before any values are stored in the circular buffer. And let's just check for any available data right here. And I'll just copy this and place it after every line of test code. Now let's simulate it. Again, I'll delete the last watched item to add the available variable. And I'll add the test buffer back to the end of the watch list. Now we can see the two indexes, the temporary data and available variables, and the first 3 bytes of the buffer. First, we'll initialize the buffer. Then we'll check how many bytes are available, and notice the 255 changes to show 0 bytes available. This is correct since we haven't added any values to the buffer yet. Now we'll add the value of 10 to the buffer and check how many bytes are available. It should be 1, and it is. We'll add 8 to the buffer. Now there should be 2 values stored, and there is. Next, we'll take the first byte out of the buffer, which is 10, and our available bytes should now be 1. And look at that, it's 1. Then we'll add 13. Now we should have 2 bytes stored, which is what we get. Now let's reset and restart the code execution to test the wraparound capability. Notice that these values did not reinitialize to 0. So in this case, since we're using a local variable for the buffer, we need to use the initialization function. I'm going to show the last 2 bytes in the buffer at indexes 254 and 255, along with the index values, data, available, and the first byte of the buffer. Now, after I initialize the buffer, I'm going to change the values of the indexes to 254, so we can test the wraparound from 255 back to 0. Now, if we check what's available, we get 0. And the first value of 10 is stored at location 254 in the buffer, while the right index incremented from 254 to 255. Now we have 1 byte available. We'll place the next value of 8 into location 255. And notice that the right index properly wrapped around from 255 back to 0. And we now have 2 bytes available. We'll grab the value of 10 from the buffer, which increments the read index to 255 and now gives us 1 available byte. We'll put the value of 13 into the buffer at index location 0. Notice it wrapped around from 255 to 0. And finally, we should now have 2 bytes available. Perfect! Now remember, I said we don't need to initialize the buffer if it is defined as a global variable. All C compilers should initialize global variables to 0. Let me know if you know of any that don't. I'm going to move our variable definition outside of main to make it a global variable. Now, I'll just get rid of the initialization function since we shouldn't need it. And let's simulate this. Now we have some non-zero data in the variables. Then I'll reset and restart the execution. Notice that the indexes and buffer data are all back to 0, so initialization isn't needed for global variables, unless of course you don't want them initialized to 0. So that's it. That's how easily we can implement a simple circular buffer. And you could even test this out further. Convince yourself that it will work under all conditions. Also, these functions can work on more than one buffer in a given project. Just create separate variables for each buffer you need. One thing to note about this implementation of a circular buffer is that although we have defined an array length of 256, we can only store up to 255 values in this buffer. That's because if we try to fill all 256 bytes of this buffer, then the write and read indexes will be the same value and the data available function will return 0. If you really need all 256 bytes for storage, then you could add another variable to the structure that holds the number of values stored in the buffer. But since I'm writing this code to be used on a microcontroller with minimal memory, I'll just use it as is since I don't plan on coming close to filling the buffer anyway. Also, you may want to create another function or two to indicate whether the circular buffer is filled or empty. I'm not going to do that since we can analyze the value from the data available function to determine this information. This is really all we need for a very simple implementation of an 8-bit circular buffer. But you can always make it as fancy as you want. You could test if the buffer is full before inserting. You could test if it is empty before reading data from the buffer, etc. You could even use linked lists if that's what floats your boat. Now that we have created these new circular buffer files, the source code and the header file, be sure to store them away for use in future projects. Well, that's all I have for today. I'll be writing some more code in future videos, and we'll try to work on some projects that use the code we've just written. Thank you for watching, and I'll see you next time, right here on Dr. Plague.